Stanford University.
CS 193P, Lecture 15, iPhone Application Development. You know the routine. Today we're going to be talking about iPhone device APIs, specifically using location services on the phone, as well as the accelerometer and the camera. So should be some pretty cool demos to go along with that. There's also going to be a little bit on kind of holistic performance, battery life, power management, all that good stuff, which you sort of need to keep in the back of your mind and occasionally in the front of your mind as you're writing iPhone apps. A couple of quick announcements first. Presence 4, as you all probably know, was due last night at midnight. If you've got late days, you know, you can burn them if you need to. They're there for you to use. We've had actually a lot of laptops. Speaking of burning, laptops go up in flames this quarter. Kind of more than normal. And you know, as we mentioned, final projects, you cannot use late days on those. So yeah, keep that in mind. A couple of lecture announcements. We just got this confirmed moments before our lecture began, but this Friday's bonus section is going to be with NG Moco. Not quite sure what exactly we're going to be covering, but hopefully it's going to be something OpenGL related. So if you're writing a game, or if you're interested in writing a game, or anything else that might want to utilize OpenGL, it should be a pretty cool talk. They make some great iPhone games. And then I just want to give you a heads up on the sort of upcoming in-class lecture slate. It's a little bit different from the syllabus on the website. Obviously, Monday is Memorial Day, so there's no class. Wednesday, we're going to be discussing audio playback, video playback, and web views on the iPhone. Alice is going to be giving that lecture. So if you're doing any of that sort of stuff in your app and you want to know how to do it, that'll be the place to be. It's another fun lecture full of demos and lots of good stuff. On Monday, June 1st, we're going to have another special guest, Dr. Go Wang. It's Go, right? Yeah, is going to be coming in and talking about all sorts of cool stuff. He's the kind of the driving force behind ocarina, leaf trombone, who knows what else in the future. So that is not to be missed for sure. And then finally on Wednesday, June 3rd, I'm going to be talking about some assorted Objective-C topics, some fun stuff that you know, isn't going to really relate to your grade in the class, but it'll just kind of be an interesting note to end the quarter on. With all that, any questions, logistical stuff? We're good to go. All right. So I'd like to introduce today's guest speaker, another guy from Apple. Justin Santamaria works on iPhone software engineering on a variety of things, and today he's here to talk about device APIs.
Thanks, Evan. So today I'm going to cover a variety of topics. The first are some of the hardware APIs for the iPhone OS platform, image picker, core location, and the accelerometer. And the second topic I'm going to cover in the second part about battery life and power management, and how you can consider these factors when writing your application, and what you can do in order to optimize these things for the iPhone platform. So the iPhone has a lot of cool features, and it's part of the reason why I work at Apple and why I work on the iPhone. I've been working on the iPhone for the past 2.5 years, since before 1.0, and it's just been a great thing to work on. And now with the SDK that's open for other people, and we've seen a lot of great apps on the App Store that utilize some of the unique features of this platform. And some of the things that make it unique and fun to use are these hardware things. So on every iPhone is a camera, a 2-megapixel camera, and we want to expose that for you developers to be able to get data from. We also have a thing called core location, which allows the phone to know exactly where it's going to be, where it is at a given point in time. And we have accelerometers, which allow us to do things like detect orientation changes from a portrait mode to a landscape. For instance, in the iPod application, we can go from the album view to a cover flow view through a simple gesture, through a simple rotation of the device. Also, we've seen many cases on the App Store with games that actually use the accelerometer as an input device. With, you can swipe and do all sorts of cool stuff with the actual movement of the phone as input. So all these things are related, to the hardware and are pretty tied to the hardware. So in many cases, there's only limited hardware support. And so throughout this lecture, I'll let you know when some things are going to work on the simulator and when some things are not. So you're not bashing your head against the wall for too long wondering why this thing isn't working in the simulator if you're trying to make it work. So let's start with the image picker. So the image picker interface kind of looks like this. It actually does look like this. When you have a camera, you can go ahead and take a picture with the picture button and hit cancel. There's also 3 different interfaces for the image picker. The first is the camera, which is available on every iPhone. There's also the saved photos role, which every photo that is taken by the camera application gets put in saved photos. Notice if you also want to save photos to the photo roll, you can do that as well. And the reason you might want to do that is so that the user can actually get that photo data off the device and onto his or her Mac or PC. Because this save photos roll is just like a photo roll from a camera. When you plug it into a computer, it can download those photos. So we'll tell you how to use that a little later. And finally, there's the photo library. And what this is a collection of photos that is stored on a user's computer and synced over to the device so that the user of the device can actually have their photos with them on the go. Now, the image picker interface allows access to all 3 of these things so that when you want to get a photo from a person, you can present the option of either choosing from one of these 3 things. So let's get right into how you do this. So what you use is a UIKit class called the UI Image Picker Controller class. You use it as is, so you don't have to subclass. You're just going to instantiate it in your uController and go off to the races. This handles all the user and device interactions, and it's built on top of UI controller. So what these 2 things mean is, one, you have what your app does, and you don't have to worry about the gritty details of firing up the camera and wondering if it's ready or anything like that. You let the UI Image Picker controller do that for you, and you take control back once the user has selected an image, however they decided to do so. UI View Controller is important because, as you've probably seen throughout previous lectures, this is a really powerful paradigm that allows you to actually compartmentalize bits of functionality and allows you to really kind of not worry about specific things, and it slides right into your application very nicely. So UI Image Picker Controller definitely takes advantage of this. The other thing this allows it to do is that all apps have a very similar, in fact the same, image picker interface. So the user's not confused when the picker slides up from the bottom, because every application does this. So how are you going to get images back? Well, you're going to need to implement the UI Image Picker Controller Delegate Protocol. You probably realized Objective-C is a bit verbose, and that's one of them. It's implemented by your delegate object, and it has a couple of methods that you need to implement in order to get back data and continue on with your workflow for your application. So now that we kind of know what classes we're dealing with, we need to figure out the steps for actually using this. Now, the first thing you want to do is check for the source type. And the reason you want to do this is because not every iPhone application has, not every iPhone OS piece of hardware has a camera, for instance. iPod Touch doesn't have a camera. So if you have a Take Photo button and the user presses it and they're not in an iPhone but on an iPod Touch, that's not going to work. So you're going to want to check to make sure that the source type that you want the user to use is actually available on their device. The second thing you want to do is assign a delegate object. And what that's going to do is that's going to allow you to receive the callbacks from this controller once it's done processing or done interpreting the user input. And finally, you want to present the controller modally so that the user can actually interact with the UI Image Picker controller. So this is one example of what it could look like. In this block of code, you can imagine this is in some view controller code. The first thing it's doing is checking to see that the camera source type is available. So you can imagine this is a take photo button or something like that in an application. Now, if this is on an action, what could happen here is the user presses the button and nothing ends up happening. So you could actually move that logic up somewhere else in your app to maybe hide the button altogether or give it a different source type like the photo library or something like that from the user to pick from if there's no camera available. But assuming that there is a camera on this device, it drops into this block where we allocate and init the UI Image Picker controller. We set the source type to camera so that when the picker comes up, it comes up in the camera mode. And then we set ourselves to the delegate. So this is assuming that this particular object implements the delegate methods. And we'll get the callbacks from the UI image picker controller. Finally, we want to present the modal view controller. And animated's nice, so it looks nice and clean there. And what this will do is it'll allow it to animate from the bottom of the screen up. At that point, the user is going to get an image, and once they take a picture, they get to something like this, and they have a couple of options. They can cancel the picture or choose. And these two buttons pretty much are exactly parallel to what the methods look like in the protocol. So the two methods are image picker controller did finish picking image, editing info, and image picker controller did cancel. So if the user selects choose, you get the first callback. The user hits cancel, you get the second callback. Now what do you do? So it's actually pretty straightforward. If the user selects choose, this gets called. And what we do is we get an image. We have an image argument, which comes back as a UI image object. And that's the actual image that the user selected. We're not going to worry about editing info just yet, but we'll get into that. Now what you can do here is you can do whatever you want to do with that image data. You can draw mustaches or what have you, or save off the image. Now it's really important that you realize that image data is kind of big relative to the phone's capabilities and hardware. So if you have a lot of image manipulation to do or a lot of calculations to perform, your app might appear to hang if you're doing it right in this part of the callback. So if you're doing some sort of complex image manipulation, you might think to spawn a thread and send that data over to that thread so that you can keep the flow of execution on the main thread going so your app doesn't appear to hang. Even saving an image takes about a second or two. A 2 megapixel image on the iPhone takes about a second or two to save. And there's some ways we can get around that too by using threads or asynchronous functions, which I'll show you in a minute. Finally, once you're done using the image, saving it off, whatever, you can dismiss the modal view controller, and you probably want to dismiss it in an animated fashion, so it slides back down. And then you can release the picker. If the accept case was easy, the cancel case is even easier because all we need to do is dismiss the controller. There's no data to manipulate. The user didn't select something. So it's as if nothing happened. And you can get rid of the picker by releasing it. So that editing info comes into play here. There actually is a property on the UI image picker controller called allows image editing. And if you set that to yes, what that does is allows the user to actually crop the image, to zoom it or pan it around, and actually select a segment of the image out of the picture they selected. And there's metadata now in the NS Dictionary editing info. So what happens is they get this move and scale panel, and they can actually move that image around, pinch and reverse pinch. I don't know what the technical term for that is, and slide it around and select the actual segment or subsection of that image. And so that comes down in editing info. The image that is returned here is actually a crop of that image. It is actually the it's a cropped image. And what editing info returns are two key value pairs. The first is the UI image picker controller original image key, which will actually have a UI image to the original image selected, the uncropped image. And the UI image picker controller crop rect, which will return coordinates, a rect, basically, of the actual crop of the original image. So you can actually use the original image data and do that manipulation however you want. So you get all the data back, even if the user crops the image. A note to all of this, and I'll talk about this later a bit extensively, is you want to avoid retaining image. We're on a mobile device. It's got constrained memory. So you definitely want to do what you need to do with that image you get and get rid of it, release it. Because the more images you retain, the more memory your application is going to use. The more memory your application uses, the more constrained the environment's going to be, and the more likelihood that you're going to start receiving memory warnings. And if you still don't if you still don't release those images, you're going to be asked to leave the dance. And we don't want that. we want your apps to run. We don't want customers wondering why your app's quitting all of a sudden. And it's because you don't want to keep these large images around in memory, because you will find that you will start to hit those memory warnings pretty quick. So do what you need to do, and then get out. So as far as saving images is concerned, there's a function UI image write to saved photos album. There's a function, yes. And photos can be downloaded to iPhoto by the user, as I said before. There's equivalent apps on the PC. And there's a completion callback. And what the completion callback allows for is if you call this method and provide a function, excuse me, and provide a completion callback, what's going to happen is the user is going to be able to I'm sorry, you're not going to hang right there. It's going to continue this thread of execution, and you can display a progress bar, allow the user to continue execution of your application, and you'll get a method callback on your application to indicate that the saving is finished and you can stop the progress bar or what have you. So this is kind of a nice little polished thing, so your app just doesn't hang for a second and a half while it tries to save. So most all of this stuff is available in the simulator, with the exception of the camera source type, which is actually kind of a good exercise because your app should be able to run successfully without the camera source type. So that's a good check. But everything else, there's a camera roll, and there is a photo picker. There is a image library. In fact, there's a stock one on the simulator. It's like of someone's graduation or something. So you can check that out and actually integrate that into your app just fine. It should work just great on hardware. Are there any questions about the image picker? It's pretty simple, pretty straightforward. So some key tips real quick. Remember to always check the source type availability. You also want your delegate methods to do the cleanup, meaning the third thing, be frugal with your images, release them when you're not using them and when you're done with them. Don't forget to release the image picker controller, and that this stuff is available in the simulator. All right, now let's talk about core location. So you might be asking, or not, what is core location? Well, core location is the thing that allows that blue ring there to show up in Google Maps. You hit that activate service, and core location fires to life, and you get a location ring. Now, let me be very clear here. Core location doesn't provide map data. It doesn't do any drawing, anything like that. It simply provides the object that provides the coordinate data that allows the application to draw the location ring. So how does it all work? Well, there's actually a three-pronged approach to core location on some devices, a two-pronged on others, and I guess just one on touch. The first is cell phone tower data. If you have an iPhone, your iPhone is likely connected to a cell phone tower, and it knows what cell phone tower it is, and there's a big database in the sky that says where that cell phone tower is located. So the iPhone can go query that cell phone tower database and come back with some coordinates of where that is. And that's usually good to about 1 kilometer or 1,000 meters, okay? The other way it does it is through Wi-Fi hotspots. And in much the same way, there's a big database in the sky of where Wi-Fi hotspots are located. And if your iPhone's near some of those and you have core location activated, it can query this database trying to figure out where those Wi-Fi hotspots it detects are. And this is usually good to about 100 meters. And then there's the big one. There's the actual GPS satellites. iPhone 3G has GPS capability, a GPS radio that can receive data from GPS satellites. And this is good to about 10 meters or so. So that's pretty close. A little close for comfort if you ask me. But you may want that, and that might be good. And you may ask yourself, well, on iPhone 3G, if it has a GPS radio, why do we bother with the other two even? And it turns out that these technologies actually do provide roles that are helpful to have all three. The first is Bootstrap. It can take a while for the GPS radio to fire up and synchronize do all its math and calculations and meet up with the satellites and get all those signals, enough signal in order to fix a location. So in the meantime, if we already have a general idea of where you are via the cell phone tower interface, we can vend that to the application right away or near instantaneously. The other thing is a cross-check. Nothing's perfect, and a satellite could be acting up, or there could be an errant DB entry, or someone could have moved a hotspot. And so using the three technologies in tandem allows us to catch those errors and provide the most accurate data possible. And the third is they complement each other. It turns out that there are varying degrees of accuracy that all three of these technologies provide. But additionally, the level of accuracy that this has is directly related to the amount of power it takes to use each of these technologies. So what we did, yes?
I just have a question about the Wi-Fi database.
Sure.
Only public Wi-Fi hotspots, or does that include private Wi-Fi?
Yeah, it includes private hotspots. It's pretty cool, actually. I'm surprised. Yeah, you can imagine a big truck that drives around and scans it. But I mean, that's the wireless world we kind of live in these days. Yeah.
It's not just using the IP address.
The IP address of. I'm sorry. Yeah. So he's asking about the Wi-Fi database in the sky and whether or not it uses private or public hotspots, and it indeed uses both, because the very nature of Wi-Fi has hotspots broadcasting some sort of ID in order for laptops and whatnot to be able to see them and connect to them. So that data is just kind of there. Now that doesn't mean that it's logging into those hotspots or doing anything like that. It just knows that there is a hotspot with a unique ID there. And with that unique ID, you can assign a location to it. So that's kind of, in a nutshell, how that stuff works. So we took all this and packaged it into the core location framework. So, and the whole point of that is so that you as a developer don't have to really worry about all the technologies I just explained and the intricacies of looking something up in a database, or wondering if there's, if there is GPS line of sight available or not, and switching to the phone-based cell tower signals to get GPS coordinate data. Like, none of that is anything you should have to worry about. All you should need to do if you want to use core location is to be able to get location data when you need it. So that's exactly what this framework tries to do for you. So there's a really straightforward paradigm here. The first is the CL location manager. It vends CL locations that you get via CL location manager delegates. So it's really straightforward. Let's look at the delegate. The first method is when you get a location. You get the location you updated to and a location that that the core location manager was last aware of. And when it fails, you get did fail with error. Now, this is one of those frameworks where we have to care about failure. There's a lot of temptation, I think both in university and in industry, to kind of hope for the best case. But this is one of those cases where actually you're going to need to specifically handle failure cases. And I'll go into why in just a bit. These callbacks are made asynchronously on the main thread and issues movement-based updates. Now, other platforms and other systems, GPS systems, don't necessarily issue movement-based updates. Some tend to issue time-based updates, meaning you get a GPS location, or I should say a location, at a fixed interval, every 5 seconds or every 10 seconds. Core location doesn't work that way. Core location calls the did update to location whenever it has a new location to vend. So they can be very irregular. If you're not moving at all or very little, you may not get a location update for an undetermined period of time. So you're not going to be getting regular updates. Now, what does that mean? That means you shouldn't be depending on some sort of UI update, like if you have a pin and it kind of pulsates, kind of like on the Google Maps on the iPhone 3G. You don't want to depend on having that method called in order for you to do the pulse. You should create a separate NS timer that fires on a regular interval to do that sort of animation, because these tend to be very irregular. Okay? So how does it look in code? We allocate an init, a CL location manager. We set the delegate, and we tell the location manager to start updating location. Pretty straightforward stuff. And then you start getting these callback, location manager, did update to location from location. And what can you do with that? Well, you can get coordinate data. I don't think that's a surprise, considering what this does. And you can do whatever you want with it. You can stick that pin on your map. You can also see how recent that location is. So if there's another application running, say Google Maps is running and your app is running, you may have a cached location already available. And we will then to you that location right when you start updating location. So you might want to check to see how old that time interval since the last location update was. And if it's, in this case, it's 10 seconds, but you can imagine that maybe 10 seconds is a little aggressive, but maybe a week or a few days might be something you want to throw out and wait for the next update before you do any sort of calculation or manipulation of your view based on that data. The other thing it returns is horizontal accuracy. And this lets you know to within what radius is the coordinate you're getting accurate. And you can kind of, if you think about it, that kind of ties into the Wi-Fi hotspot or the cell phone tower coordinates, because those aren't as accurate as, say, the GPS data. So you can kind of probably guess what kind of data you're getting depending on what your horizontal accuracy is. But it also turns out GPS data tends to be very, very, well, relatively inaccurate at first, and then it gets more and more accurate. So you can't always know exactly what source you're using. But that's not really important. What you need to know is the horizontal accuracy. Now, it's really good to be able to filter this stuff out, because maybe you don't want horizontal accuracy, or maybe you don't want, or maybe you do want a specific horizontal accuracy, or you want a specific timestamp, or you want something like that. And that's great, but it'd be great to tell core location that, so that it can optimize its power consumption. Because let's say you're doing some sort of application. Let's say you're looking for like all the new home sales in El Paso, Texas, for instance. You don't really need a super accurate location fix. You need like a regional fix. And so it'd be great to be able to tell core location up front, I only need accuracy within 3 or 4 kilometers. And that way, core location doesn't have to fire up perhaps doesn't have to fire up the GPS radio. So how can you do this? Well, you can set an accuracy level, and there's higher and lower accuracies. There's an enumerated type there. And so when you allocate and init the location manager, you can set a desired accuracy. And this just is a hint to core location to the kind of accuracy you need. You can also change the accuracy setting later. So let's say you have a globe application, okay, and it displays a globe of the world. And at the most zoomed out level, you have the pin of wherever you are. And at the most zoomed out level, that pin is probably the size of the United States. And you don't need the best location at that level. In fact, once you zoom into the United States, the best level you still don't need. I mean, if you're within 100 miles, you're still good. It's only once you get into the regional and into Santa Clara and into the Mountain View, Palo Alto, Stanford area that you're going to want to up that accuracy. And so if you when you're designing your apps, kind of think about this, try and think about this and see if you can't adjust the accuracy of the data you want back as the user interacts with your program. The other thing you can do is set the update threshold. And this, again, is in distance. So let's say you have a weather program, and you're just trying to see the weather for the area you're in, for the San Francisco Bay Area. Well, the weather doesn't really change that much, depending on how far away you are. It doesn't matter if I'm 10 feet away, the weather's probably the same. In fact, it doesn't matter if I'm 100 feet away, the weather's probably the same.
What are the units there?
The units here are meters, yes. So, it can be a few kilometers before you may want to get another distance update. So really be thinking about, if you're going to use core location, the nature of your application. Because it might be that, whether I'm here or right over there just doesn't matter. And you can really save on power and on the time it takes to actually fix a location that you want if you do that.
What's the default behavior? Does it jump jump straight to GPS if it's...
You know, I don't know. I'm sorry? So he was asking what the default distance is, and my
Actually, the battery life.
oh the what do you mean?
Or desired accuracy, because you know if you want to conserve battery, then you don't use the GPS. Basically, you use the...
Oh, right. So I believe the defaults here are on the higher end, because but you know what? I would have to check the documentation for that, because I don't know just right offhand. The question was what the default settings for the accuracy were, if you don't specify the accuracy. So that's a documentation lookup. I don't know offhand. So let's say you're done using your app, or you're done with core location anyway. You've got a fix, and that's something that is also helpful. Let's say you do have a weather application. To go back to that example, you don't necessarily want core location continuing to fix on a position, because once the users open the app, chances are they aren't just flying to the next spot right away and keeping the weather app open and wondering if it's going to update. So once you get your fix, once you get your location fix, go ahead and stop updating location. Your app's done using core location. It doesn't need it anymore. It's also important to note that you can restart this later if you need to. So you don't need to tear down a location manager and bring it back up in order to start getting updates again. Now, when might you want to start and stop updating your location? Well, if you have, let's say, a social networking application or something that you're building, and one of the features is a map and it shows you where you are relative to where all your friends are the last time they logged in, that's great, and you know, I'm happy for you. But if they switch off of that screen, say to post on someone's wall, upload a few photos, stuff like that, you don't really need core location vending you any more location data. Once they've left the location screen, that data is coming back and you're basically throwing it away. So you might want to stop updating location, and then when the user comes back, if they decide to come back to the map, and start updating location again. Yes, sir? So the question was the alert that comes up when you fire up a core location enabled application, and that's something I'm going to get into in a couple slides. So if you hang on, I'll probably answer your question. And here we go. So if you don't get a location fix, or we can't get a location fix for whatever reason, you're going to get a location manager did fail with error. Now, like I said earlier, this is something you definitely want to deal with if you're writing an app that uses core location. You definitely want to, because there are so many reasons that it can fail legitimately with a perfectly functioning device that it would be a little amateur hour not to deal with it. Like you want your app to actually respond to these things. And a very common legitimate reason is these KCL error denied error. So any app, when it first asks to start updating location, the system itself, this is built in, this is nothing that the app writer has done, the system pops up with a dialog that says, this app's going to use location data. Do you want to allow it to use this data? And the user has the option of denying it or accepting it. Hopefully for your application, it makes sense why you might want to use location data. But instead of assuming that only people who will legitimately use this API are going to implement it, you take an approach of having a whitelist. And basically, to get on the whitelist, the user has to accept your location, accept that the app will use your location data. So that just happens automatically. And if it gets denied, if the user hits don't allow, you get a KCL error denied error. And if they allow, then you'll start getting updates, assuming that updates can be had. Yes, sir?
Does that happen the moment that you init a location manager?
I believe that happens when you start updating location. When you first start saying, I want to get data. The question was, when does this pop up? At what point in the initialization of the CL location manager does this alert pop? And I believe it's when you start updating location. Okay? So that's one reason. And in this case, if they hit don't allow, instead of just making your app look like it's hanging, you might want to display some disabled look or some, hey, this is a location-based app. Please allow me to access location. But if you're an app where getting a location fix isn't critical, you should still be able to function perfectly normally. Another very common location is that the error is that a location may not be available. And in that case, you get a KCL error location unknown. A perfect example is when you go into a tunnel or a parking garage. Parking garages don't tend to have Wi-Fi, and they don't tend to have cell signal, and they don't tend to have line of sight to GPS satellites. So if you're in a tunnel or in a parking garage, you might get one of these, or even if you're out in the open, something might be happening that you can't get a signal. And it's likely just temporary. But you should but this vents you so that you know that you're not getting a location. So you either need to continue your application flow, or you need to display to the user that location, is disabled for whatever reason, or is disabled, so the user's not left there wondering why the app doesn't appear to be working, or at least why the location piece of the app doesn't appear to be working. It's likely just temporary, and there's nothing that you need to do with the CL Location Manager. In fact, once a location can be fixed, say they come out of the tunnel or out of the parking garage, you'll start getting the DID updates. So you don't really need to mess with the location manager. This is more for you so that your application is kind of in the know with what's going on. So as you can imagine, core location has limited simulator support. You're able to compile against those libraries, but it's you're not going to get meaningful data coming from those delegate callbacks or anything like that. Any questions about core location? Yes, sir.
You probably had it on one of the slides, but what's all the data that you get back with position?
So
Latitude,
there's latitude, longitude. There's I believe there's altitude, but that's also that like for instance the cell phone data and the Wi-Fi hotspot data doesn't have altitude, and the GPS data can even be spotty at that. You have your horizontal accuracy. You have there was one other, and horizontal accuracy, and the timestamp. That's right. All right, so let's move to accelerometers. So what are accelerometers? There's these things in the phone, these little pieces of silicon that measure changes in force. So if I have a phone and it's just up like this, there's a force exerted in the downward direction. Okay? And this little wafer here can detect that. And then if I rotate the phone, there's force of gravity in two directions. And so we can tell what orientation the phone is in based off of that. So what are some of the uses? Well, Safari has one use where you have Safari in portrait, and you have a nice looking a web page there, but then you can put it in landscape. And this is detected by the accelerometer. An event goes through, and the interface rotates. And you get a wider view, great for reading articles or whatnot. Another way is in the iPod application. Like I said earlier, you can go from the album view to a cover flow view. And then there's also, like we'll talk about in a bit, games that actually use it as input. So there's two kinds of orientation. So we're going to talk about orientation before we talk about input. There's the physical orientation, which is how is the actual physical device positioned. And then there's the interface orientation. And the best way to think about interface orientation is where is the status bar? Now, this is kind of maybe a little kooky, so it's best to give an example. Let's take the Photos app. So we're in our photo albums, and I select a photo. It's my mom and sister. If you notice here that the title bar is at the top, and it's portrait, and so is the device. But if I go and rotate it, what happens here is the device is in a landscape position, but the title bar is still in a portrait position. Okay? So here the device orientation is landscape, but the interface orientation is portrait. Okay? Similarly with Safari, if we take the portrait Safari view and rotate it, its interface orientation goes landscape, and so is the physical orientation. So those are the two differences. They're there, and so that's when you're dealing with interface and when you're dealing with the actual physical orientation. So if you want to get the physical orientation of the device, you can ask the UI device class. And you can start notifications by calling begin generating device orientation notifications. And you can get the orientation by registering an observer for the notification UI device orientation did change notification, which is delivered to register observers. or you can get the orientation property off of the UI device class. And again, this returns a device orientation. You can stop notifications by calling and generating device orientation notifications. Now, getting the interface orientation is off the UI application class. You can get it by calling the status bar orientation property. And again, this defines the interface orientation. Or you can use UI view controller class, your UI view controller, and ask for the interface orientation. You can also enable automatic orientation of your application by implementing should auto rotate to interface orientation and implementing a couple other methods in your UI view controller, and it kind of does it for you. But I won't get into that today. So orientation changes are really nice. It's nice to know if the phone's in portrait or landscape mode, but what we really want is the raw data from the accelerometer. And when we talk about raw data, we're usually talking about using it for some sort of game or input device. And so when the phone's shaking and shimmying or whatever, using it as a steering wheel, you want that data coming in a constant flow. You don't just want when it goes portrait and landscape. So we've created an interface just for that called the accelerometer interface. And it's part of the UI kit framework and delivers 3-axis data and has a configurable frequency from 10 to 100 updates a second. And it gives delegate-based event delivery like the other two device classes that I've just talked about. So let's get into it. So first of all, this is the axis orientation of the phone. The Y runs up, the X runs to the right, and the Z comes at you. Okay? And I'm not going to right-hand rule you, so don't worry. It's just those are the axes. So getting the raw accelerometer data, this is a familiar pattern. You get an UI accelerometer that vends a UI acceleration object, and you get via a UI acceleration delegate protocol. So how do we do this? Well, we start the event delivery by, we don't create an accelerometer. There turns out there's only one accelerometer per application. So we grab the singleton, the shared accelerometer, by calling UI accelerometer shared accelerometer. We then set our update interval. In this case, we're sending it to 50 hertz. And then we set the delegate to be ourselves so that we can get the callbacks. And then you're wondering, where's step 3? Where's the start? Well, there is no step 3. Once you set your delegate, the event delivery begins. Okay? So all you do is set your delegate, and you start getting accelerometer data right away. So what do you get? Well, if you implement, which you'll need to, accelerometer did accelerate, you get an acceleration object which holds acceleration values in the X, Y, and Z axes. From there, you can process that data and do whatever you'd like with that data. It's important to remember there's only one delegate per application because this is a shared object, the UI accelerometer object. So if you need to if there are multiple objects that want that acceleration data, it's on you, the application programmer, to disperse that data and vend it to all the objects that need it. Also, this is delivered asynchronously on the main thread, so if you want to process this data off thread, you're going to need to shuttle that off to that thread. So in configuring the accelerometer, it's important to set an appropriate update frequency. So the system range is approximately 10 to 100 hertz. That's what it can handle. And it should really be dependent on your need. And we'll go into this later on when we talk about battery life. But you don't want to update it too much if you don't need to. And so some rules of thumb are if you're just detecting something like orientation, something that doesn't happen very often, something that is more of a trying to detect constant motion, constant acceleration, you should use approximately 10 to 20 hertz. And if you're trying to do something like a game and detect fast movement or quick movement, you should up that to about 30 to 60 hertz, which is the frame rate of the device. So when you're done using the accelerometer, you stop event delivery by setting the delegate to nil. And then you're done. There's nothing to release because, again, it is a singleton object. Now, something that makes accelerometers useful is to use filters to isolate the raw data components. You can use a low-pass filter to isolate constant acceleration, like gravity. Low-pass filters are used to find the orientation of the device. High-pass filters show instantaneous movement and are used to identify actual user-initiated movement, so not the force of gravity. Something like a swipe or something like a toss, which don't make a game that uses a toss, but you'd use a high-pass filter to figure out it got tossed. And so if we look here, and I'm not sure this is big enough, so if we look here by examining the accelerometer data, if the phone is just sitting on a table, just like this, we see that on the x and y axis we're at the 0 line. Then on the z axis, in that middle, it jumps down where we turned on the accelerometer. It bumps down. And that's the force of gravity right there. Okay, so that's what it looks like. And so these things are going over time. You're getting these updates over time. And so there's the 1.0g as a function of time. But if you want to apply a filter, we need to be in the domain of frequency, not time. Okay? And so the way you do that is with the Fourier transform. Now, I've never used a Fourier transform in my life. Go take a class. We're not going to talk about that today. I'll read up on Wikipedia, and then we can meet back here. What we're going to do is approximate this, though. Okay? So you can actually get really far without actually doing Fourier transforms and actually get the data you want. So don't panic up here. I saw you guys. Okay, so here's what it looks like. So gravity's just right there in the middle, chilling out. But if you shake the device, what's going to happen is this nice little calm, serene scene changes. And it looks like this. And if you notice the x and the y are still centered, but the z, if you notice that wave, it's kind of shifted down. And that's because you've got the shaking plus gravity. So if you're trying to just detect a shake, you want to get rid of that gravity. If you're trying to detect gravity, vice versa. So it kind of looks like this when you convert it to a frequency domain. And you may be interested in that shaking, the motion, or you could be interested in gravity, the thing in the middle. So let's say you're interested in that, what's shaded there in orange. So what you can do is apply a low-pass filter. And a really, how should I put it, engineering way to do that, because it's definitely not scientific, is simply apply a lower threshold to new values coming in. So if there's sudden motion and in your new value, its effect is minimized over time. And really the aggregate is what gets added up. So you get the effect of nilling out any of the jitters. And it works pretty well. The opposite of that, doing a high-pass filter, where you want to get rid of gravity and just get those jittery components, can be done in much the same way. In fact, what we do here is we take the acceleration value that you do get and subtract out what would be the value of the low-pass filter. So that's kind of a neat trick there. And so I'm going to show you something here real quick, because you might say, that doesn't look legit. For those of you who think that, I didn't write that. OK. So here, let's see here. Movie recording. So we don't have a projector in here. Hi. So let's take this app here. I'm going to hold it up to the camera. And so this is using a low-pass filter. And if you notice, it's getting pretty smooth data. And in fact, if I shake it a little bit, it's just smooth. It doesn't care. And this is using that algebra we used. It's actually pretty good. And that's because it's getting plenty of updates per second in order to be able to do it. So let me just go over here. And this is what it looks like. That's the one focusing on gravity. That's correct. So yeah. So if we look here, we basically are applying that low-pass filter to both the x and the y coordinates, then doing a little trig, and then sending that to the view in order to display in a nice way. And that's it. It's really straightforward. And it actually produces exactly the effect that you'd be looking for. Now I want to show you one more thing. And that's the use of a low-pass and a high-pass filter. This is called an oopsie daisy. And so we got this daisy here. Hope you can see it. And it's kind of, if you notice, there's an open source physics library this is hooked up to. And if you notice, the daisy kind of moves to wherever gravity is. It's got a little bounce in it and whatnot. And so that's using a low pass filter. And the thing is if I shake it, the petals can fall off. And so that's being detected by the high pass filter. So you see that? Boom. She loves me not. She loves me not. All right, well, we'll just leave it there and not worry about it. So that's an application of both the high and the low pass filter. Oh, so the question is he saw an ATAN2 function in the sample code and whether we want to include, if we need to include math libraries. And the answer is, if you want to do math on it and do ATAN2, you're going to have to include math libraries. But I think that's in math.h. So I don't think that would be, I think that's fairly trivial, actually, to include. You know what? The question was, what was the name of the physics library? And I'd have to look it up. That was written over a year ago, so I don't quite remember.
We can probably post the code.
Yeah, we'll try to post the code to the site if we can. OK? So it's important to note that the accelerometer doesn't have simulator support. We don't want you shaking your laptops around, because while that might be fun, ultimately it's sad. There's still moving parts on the laptop. Maybe one day, but not today. So we didn't build that in. So some key tips toward using accelerometers effectively. Use UI view controllers for the orientation. It's built right in. Use filters to isolate your raw data components. That way you can get meaningful data back and figure out exactly what you want to do with that data. And then disable the accelerometer updates when you don't need them by setting them to nil. So in summary, for the device API portion of this lecture, remember to take advantage of the device APIs. But for image pickers, always check the source availability, because not all iPhone OS devices have every source. And for hardware-based features, turn them off when they're not needed. And that dovetails perfectly into battery life and power management. Do we have any questions about device APIs before I continue? So power management. We're working with a mobile device here. And small devices need advanced power management. Now, when you think about a laptop, or let's say a desktop in my world where I work is like infinite power. You know, it's plugged into a wall. If it needs more power, it just takes it. A laptop, a little different, because it actually does need to run off a battery. So how much power does a laptop consume? Well, in general, about 20 to 60 watts. And you think, what's 20 to 60 watts? You figure that's about a light bulb. Light bulb can be like 45 watts or so. Incandescent bulb. So, OK, I know what that is. Well, how much does an iPhone device use? Well, it turns out it's about 500 milliwatts to 2.5 watts. And when I say 2.5 watts, I mean you have everything cranking. You've got a movie playing, you're looking at GPS data, and you're doing some complex math algorithm. Like that means you're watching your battery meter just tick down. So it's never at 2.5 watts, or rarely, I should say. So it's really on very, very little power. So we need to do some things in order to minimize power consumption. One of the things we do is dynamic clocking. And what that means is when you're not using a CPU or a GPU, we turn down the speed, and that saves on power. And we do that as often as we can. Another thing we do is we clock gate and power gate. We turn on and off blocks of chips every chance we get. And the reason we do that is if you're not using it, if it's not in use, we shouldn't have it on. And that's why the iPhone is able to get any sort of battery power at all. So what consumes power? Well, it turns out everything. Everything you do on the device consumes power. Now, there's different levels of power consumption. The radios are about 2 watts. So this is the biggie. I'll do them in order here. And really, these values are more to give a relative sense of how important something is. So when you're looking at your application, you can actually troubleshoot the things that are the biggest ticket items. What do radios include? The baseband, the Wi-Fi, Bluetooth, and GPS. Okay? What is the baseband? The baseband is the piece of hardware that communicates with the cell phone towers. That's what we call baseband. So all of these, when they're on, they consume a lot of power. Second in line are the CPU and GPU. The display takes up about 200 milliwatts of power. And if you'll note, in my upcoming slides, there's really not a whole lot you can do about optimizing display performance, so don't worry about it. But it's there just for comparison's sake. And finally, the hardware modules, like your accelerometers and your cameras and whatnot, take up tens of milliwatts. The biggest thing, though, is keeping the system awake and keeping it running. Because when you put your phone in your pocket or your iPod Touch in your pocket, everything gets turned off very quickly. In fact, the only thing that's left on is low power states of some of the chips like the baseband, which if you get an incoming call or SMS or something, it wakes the device up and processes it. But other than that, it's off. And that's why when you have your device, when you sleep your device, when you're able to sleep your device, it can last a lot longer. In fact, on an iPod Touch, if you don't use it and just keep it in a corner, forget you have it, you could come back to it months later and it'll still have a charge. And that's because nothing's running. So this is huge. So my message to you is to try and be very aware of your battery consumption when you're writing your application. And be aware of your use case, because we don't want to have a user running your application and watching their battery go down. So there's a few points we can take home with this and just have you keep in mind while you're writing your application. It's important to note that on the network, transmitting is the most expensive operation you can do. Receiving data, that's expensive, but transmitting data is much more expensive. 2 to 3 times more expensive power-wise. So naturally, if you can minimize the amount of data you're transmitting over the network, that'd be great. And avoiding a chatty protocol that's just going back and forth constantly, that's also good. Transmitting and receiving in bursts, what that means is basically both the Wi-Fi chip and the baseband have a way of dealing with blocks of data being transmitted. And so for a period of time, while data is transmitting, it is in a high power state. And then once that period of time is over, it goes to a low power state. And if you're transmitting in bursts, meaning you're sending a lot of data at once, you stay in that high power state, and then the radio is able to go to a low power state when you're done. But if you're sending data, and for an example, like every 7 seconds you're sending data, that chip may never be able to get to a low power state. And so it's always transmitting at full power, even if you're only using it once every now and again. But it's just close enough together that it's not able to come back down and conserve power. So you want to kind of, if you can, batch up your network activity and do it all at once. It's also important to use compact data formats, zipped formats, or compact versions of protocols if you can. And for co-location, for the GPS radio, stop the location service once you have a fix, and only request the location accuracy that you need, just like I said earlier. These things really, really do affect how long an app or a phone or iPod Touch will last under battery power. As far as the CPU and GPU, it's all about performance. So using Sample or Shark to see where your hotspots are, where you're using a lot of CPU, is the way to get to this one. Not only will you increase battery life, but you're probably going to increase performance of your app and responsiveness of your app too, because there's just a general win here by doing this. Additionally, you might want to stress the GPU less. And this is really important in things like games and stuff, where you expect users to be using them for any block of time. It's less important, say, for a weather app that someone's going to open, check real quick, and close. But if you have a big game, you might want to consider how your view hierarchies are and how many layers you've got and what kind of textures you use, because all of those things contribute toward taxing the GPU. And finally, the hardware modules, like the accelerometer. Turn them off when you don't need them. Even the accelerometer, only when you need the accelerometer should you use the accelerometer. So if you have a game that uses the accelerometer and the user's at a menu or a high scores page or at a buy armor screen or whatever, you don't need that accelerometer running right then. So turn it off, conserve some power, and then when they go back to the main screen or the gameplay screen, turn it back on. And finally, a note about the NAND. The NAND is the actual solid-state memory on the device. Try and access the disk less, and you can see how much you're accessing the disk by using the system usage instrument. There's a story where we had an app developer that was basically saving his game state out every second as this timer ticked. It would save the state of the game and commit it to disk every second. And users of his application were wondering why their phone was just getting hosed for battery life. And that was why. NAND is kind of slow and it takes up some power. Like I said before, it takes a second and a half, 2 seconds to save a photo to disk. So part of that is the NAND. So you want to kind of write to that less. Not only is it a performance win in the perception of how fast your app's going, but it's a power win. And perhaps the most important thing, if you go home with nothing else today, it's that you should let the system sleep. If you don't let the system sleep, battery life decreases tremendously. You can go from 250 hours of standby time to less than 12 hours if you keep the system awake. So how do you do that? Well, how do you hose yourself? You can disable the idle timer. Some games need to do this because they're using accelerometer input and the screen will go dark if they don't. But if you're not in the main gameplay screen or you're in a spot where sleeping's okay, please disable that idle timer. Because if that please enable the idle timer. Because that is the bread and butter. If the user leaves your app running and gets up because the doorbell rang and then forgets they were playing the app, but it's on the pause screen, and you don't re-enable the idle timer, they're going to get back to their phone. It's going to be dead. It's going to be out of battery. So please remember that. And also, don't play audio except when you need to. So the other way, I'm debating whether I should even say this, but the other way that you can keep the device from sleeping is by playing audio. And so we've had app developers that got clever and said, well, if I just play a silent audio clip while my app runs, my app will never sleep. While that's true, no one who uses those apps gets any sort of performance out of their phone. And that's because whenever that app is running, it's not going to let the device sleep. So you really, really please consider how the requirements of your app and how it interacts, and whether or not you need to even utilize these methods, because chances are for most things you don't need to. So do we have any questions about battery performance? Well, this is good. Thank you very much. I'll be here for questions if you have any. Thanks.
For more, please visit us at stanford.edu.